Hi everybody, welcome to, where's week 4 of the seminar series for 7 to 10 science. I do apologize for last week, it was definitely something out of my control. So, back on track, I will upload what was meant to be last week's, which is biology, over the weekend, and along with a load of videos. I have them all recorded on my phone, but it's just having a bit of a meltdown. So we're going to go a little further in depth into chemistry. Last when we worked on the periodic table and why things bond together. Now we're going to look at chemical reactions and what happens. So, chemical reaction makes a chemical change. And whenever this chemical change occurs, then a chemical reaction is said to have taken place. What I want you to do is spend 30 seconds thinking of a few chemical reactions that you can think of and writing them down. The thing with a chemical reaction is it can't be reversed. Generally, it can't be reversed. And something new is formed when two things come together. So, if we were to dot point it, chemical reaction equals a chemical change that's irreversible and something new is created. So, we also have physical changes. I don't really know what I was going to write on the whiteboard, but we can just speak about it. So, physical changes are different from chemical changes. If we have a log and we cut that log into pieces, these are the some of the tutorial questions, so if you want to write them down. If I cut a tree into pieces, a log, is that a physical or chemical change? Here's Jacob. Hi Jacob. I just asked if you could turn the camera off just because this is being recorded, if that's all right. Thank you. So physical changes, just to catch Jacob, physical change is something that you can see. It doesn't necessarily have the same attributes that we just spoke. So if I take a tree and I cut it down and I cut it into pieces, is that a physical or chemical change? I'm not asking to answer this question, but to write it down. It's part of the tutorial questions for this one. So, you have a tree. We've now cut it into pieces. Was that changing it physically or changing it chemically? If I then take those pieces of wood and I throw them on the fire and I burn them, is that a chemical change or is that still a physical change? We've already been through the chemical changes. Changes are irreversible. Now apply that to burning a piece of wood. If I burn a piece of wood, is there anything left? Not really. Only the carbon remains. Everything else has reacted during the fire and has disappeared. So the 5 main signs, chemical reaction is taking place. So change in color. Sorry, just as per usual. So 5 main signs indicate chemical reaction. Now what I want you to do is find that list. That's what is here. I'm Matilda. So everyone, I'll catch Matilda up quickly. Everyone has written, well, or thought of things that they think are chemical reactions. Of those things, think where a change in color has occurred, where perhaps a gas is produced, there's been a change in temperature, so think of burning wood, or a change in the state, has something turned from liquid to solid, solid to liquid, liquid to gas, so on and so forth. So for all of those, I'll give you a couple of minutes. Think of some chemical reactions where this takes place. Write them down. So, evolution of a gas. If I stick aluminium foil into bleach, the aluminium foil is broken down partly, and hydrogen gas is produced. So we've got two things here. Is that a reversible reaction? Probably not. You can't take that hydrogen gas back and put it back in the aluminium foil. Once that happens, there's no going back from it. We have the evolution of a gas. We will get the release of heat, so a change in temperature. We get a change of state from a solid and a liquid producing a gas. So, some other examples. Burning wood is an example of a chemical change. You take the wood, you mix it with oxygen in the atmosphere, you get a flame. And you get carbon dioxide, and water is released. So wood is destroyed. You get new products being formed, carbon dioxide and water. And then you have, and it can't be reversed because obviously it's bad. You can't just take it all back, put it back together. Whereas if I cut up that piece of wood, it's a physical reaction. You've changed the shape, but you haven't changed the chemical structure. So, we have a number of different ways to represent chemical equations. So, we can say the reaction of methane gas with oxygen gas to form carbon dioxide and water. So now we need to break this down. Because in chemistry, words are meaningless. Methane plus oxygen equals carbon dioxide and water. This is the intermediate step where we go from a big long sentence to 4 words and some symbols. And on the left-hand side, we have the reactants. They react together to form the products. So we have methane, which is CH4. I mean, don't worry too much about what these actually are, just where we put them. So methane plus oxygen equals CO2 plus H2. Now there's another concept. I just realized I've left my office door open. Thank you. There's another concept here. In a chemical reaction, the sum of all of the products has to equal the sum of the reactants. So you can't have more product than you did reactants. It just doesn't work. It has to balance. This balancing of equations is really, really important. I can't have 2 plus 2 equals 5. Doesn't work. Same thing in chemistry. So, and this is what we call the chemical equation. We add magnesium. So the way that this will be written is magnesium and oxygen react to produce magnesium oxide. The reactants are on the left, the product is on the right. So, must represent known facts. So you need to know how much of each, what they are, what reacts to produce what products. And they have to be in the right formulas. So 2 plus 2 equals 4. 2 of each of the reactants equals 4 of the products. So, and the law of conservation of mass, you can't create more from, so if you have, say you have a gram of reactants, you can't produce 2 grams of products. It doesn't work. The conservation, you have to have the mass of everything conserved in the products. You can create less, but you can't create more. So we also have these phases. So solid, liquid, and gas. And this is also really important for later on if you go down the road of studying chemistry, because it's an important indicator of what happens in a chemical reaction. So solid phase, substance is relatively rigid and has a definite volume and shape. My phone is a definite shape and volume. Liquid phase, it does not have a defined shape, but it has a definite volume. So my coffee has the same volume, well, unless I drink some of it, like all now. But it doesn't have the same shape. If I put that into this bigger cup, it would have a different shape inside the cup than it did in the small. So, the gas phase, no definite volume. So test this, maybe not right now, but spray a deodorant can into the air and watch what happens. Well, smell what happens. eventually the smell will dissipate because gas tries to fill the room that it's in. It'll then eventually leak through a window, and then it will try and fill the atmosphere. So eventually the gas particles get so far away that when those gas particles are by themselves, they technically don't exist. They're insignificant. And whilst liquids and solids are bound by gravity, gases typically don't really respond to it. So, and this has gone haywire with the slide set up again. Balancing chemical equations. The total mass on both sides of the equation must be equal. So, we have magnesium and we have oxygen. We have magnesium. Actually, I'll get the whiteboard out. First time. New whiteboard markers. Couldn't be more excited. So, we have so the way we do this, and this is the simplest sort of starting point. So we have 1 magnesium, we have 2 oxygen. Now the magnesium and the oxygen don't have to match on either side. It's the magnesium on this side has to match the magnesium on this side. And the oxygen on this side has to match the oxygen over here. So, the way we do that, everybody has different ways of doing it. I usually do the big one first. So, I know this is simple. There's only, if I balance this and this first, so, okay, I need to have 2 oxygen. So that makes 2 of each. So now I just have to make this 2 magnesium. And here's where a lot of people get tripped up. This here is different to this here. This is 2 singular magnesium atoms. This is 2 oxygen bound together. This is 2 magnesium that react with the O2 molecule. So you can't just add a number to the front. You have to just add an extra magnesium. So you couldn't just go, oh, okay, well, I'll just make it Mg2. No, it doesn't work like that. If you're wanting to add a number, you have to add it. Because that is 1 magnesium molecule, and now we've added a number. So everything has to balance. At this stage, I wouldn't think too hard about why, just that they do. And it might seem strange me saying don't think too much, but sometimes it's the best approach. Some a school of thinking is using a table. So you write, so hydrogen, chlorine, you would have reactants and products, and then you simply balance it. So you then have 2 HCl. Everyone does it differently. And as you go on and find your way, you'll find the easiest way for you. So, a bit more complicated one. Probably should have practiced this before I started, but you know, we'll see what happens. 2, that's meant to be a 2. So, what have we got here? We've got 1 carbon, 4 hydrogen, and 4 oxygen. Over here, so it balances. So we have 1 carbon, 4 hydrogen, 4 oxygen. So H4, CH4 means that molecule here has 1 carbon and 4 hydrogen. Whereas this is 2 molecules that each have 2 oxygen. Very different. So the number here means those atoms are bound there together. The number here, it's 2 times O2. So it's still 4, just a different configuration. CO2 and then 2 H2O. So that's a balanced equation. The law of conservation of mass says that it all has to balance. We can't have, to put it simpler, 2 grams here and then 4 grams over here. Now, when you are given a worded question, it will often not tell you what those numbers need to be. So if we look at the Haber equation, which is nitrogen plus hydrogen let's use this as a simple one. So this is nitrogen and hydrogen react to form NH2. I've adjusted what I'm going to do just for the simplicity's sake. So you're given the worded question, which is nitrogen reacts with hydrogen to produce NH2. We write it out like this. Okay, it's not balanced. All we need to do is stick a 2 in, because that is 1 nitrogen, 2 hydrogen in the reactants, and we have 1 nitrogen and 2 hydrogen in the products. Just realized I was still sharing whilst I had the still the whiteboard. So in order to balance how much of each of sodium and chlorine would I need to balance it if I was creating 2 NaCl. So write me the balanced equation for creating table salt. It's the other tutorial question. It's basically what that slide was. So we have 4 different kinds of chemical reaction. We have combination, which is A plus B equals AB. The simplest one. Decomposition, AB equals A plus B. So you're breaking something down. So single displacement reaction, AB, again, jumbled up my slides as soon as I started go. Lovely. So single displacement, AB plus CD equals so you're displacing one of those. They swap around. You can see instead of AB, it's now AC and BD. Double displacement means they completely switch around. You have displacement of all of the atoms. Then we have a redox reaction. A couple of you in a different chemistry class, I'm sure, struggle with this on Wednesday. We have redox reactions. Which involves the transfer of electrons. So the transfer of electrons through oxidation and reduction. So oxidation equals loss of electrons. Reduction equals gain. Or we could write the acronym OIL-RIG. Oxidation is loss, reduction is gain. Oxidation is loss, reduction is gain. I'm not going to go any deeper than that. Yes. So, combination reaction. When 2 reactants combine to form 1 or more products. Calcium oxide reacts with water to produce calcium hydroxide. Carbon and oxygen react to form carbon dioxide. So this is usually causes an exothermic reaction, or a reaction that releases heat. So this, and here's a visualization. 2Na equals 2 single atoms of sodium. Cl2 is 1 molecule that has 2 atoms of chlorine, and that equals 2 NaCl. So there you go. I've just given you the balanced equation for that tutorial question. So A plus B equals AB. So decomposition, single reactant breaks down to decomposition products. So 2 molecules of water are hydrolyzed and they break down into 2 molecules of H2 and 1 molecule of O2. And you'll see that they also balance. So when the decomposition reaction is carried out by heating, it is called thermal decomposition. So when you heat something down up to break it down. So, see there? Two molecules of water break down into 2 molecules of H2 and 1 molecule of O2. So hydrogen peroxide, using yeast and hydrogen peroxide, you can actually make a flamethrower with this oxygen gas that's produced. So electrolysis of water, break down to H2O into 2 H2 and 1 O2. Nitrogen triiodide, break that up back into its original products. So AB breaks down into A plus B. So we have displacement reaction. So this is when a more reactive element comes in and takes the place of a less reactive. A quick demonstration on why something is more, or not, so how you can tell which is the most reactive. So periodic table, most reactive element, fluorine, least reactive, francium. And this reactivity goes in a trend that looks something like this. So if an element is over here and one is over here and it's in a reaction, then this element will likely take the place of the less reactive element in a single or double displacement reaction. So you have magnesium and copper sulfate. Magnesium, more reactive than copper, takes the place of copper here. Double displacement, everything moves around. So calcium carbonate becomes calcium chloride. Hydrogen chloride becomes. So you've seen everything swaps places. So see that cool reaction there? So you have lead and potassium, and then potassium and lead. But you'll see that lead chloride is now lead iodide, and potassium iodide is now potassium chloride. So both of those have switched around. Oh, sorry, just one of those. Just one side has switched around. Then you've got the double displacement, where Carbonate has gone over to barium. Chlorine has come over to potassium. So this is the reactivity series. So the least reactive: gold, platinum, silver, copper, hydrogen, and then it goes up to potassium, sodium, and fluorine is at the top of that. Don't know why it's cut off. And if we look at the periodic table, we can tell what might react with what. So if we think back to our groups, and group 1, 2, 3, 4, 5, 6, 7 are all trying to get to the same configuration as group 8. So what does that mean? All of those atoms have 8 electrons, 8 spaces for electrons in their outer shell. In the very outermost bit, there's 8 spots for electrons. If there is 8 electrons in there, they're happy. So that's group 8. They do not react because they don't need to. They don't need to get to that group 8 state. Whereas group 7, so 1, 8. But 8, it's happy. It doesn't need to react because it's stable. It doesn't have any room left to react. Outside of specific conditions and specific applications, the noble gases, they don't react with it. Whereas the group 1 metals, they have 1 electron in that outermost space. So they're really wanting to go back. They're really wanting to get rid of that. So they can either gain 7 electrons from other elements when they bind to them, or they can lose 1. They're probably going to lose 1. Group 2 needs to gain 6 or lose 2. What's it probably going to do? It's probably going to lose 2. We know that electrons are negatively charged. So if this is giving away 1 electron, so let's go with sodium, it becomes +1. Na+. So group 1 always forms +1. Group 2, magnesium, when it binds with something, it wants to get rid of 2 electrons. It wants to get rid of 2 negative charges. So it will become +2. Group 3, it's for you guys to figure out. It needs to either gain 3 electrons or lose 5. So what charge would that have when it bonds with something else? Group 4, don't worry about for this. So group 5 now has 5 electrons in that outer space, and it's trying to get to 8. So instead of losing 5, it will find a metal, and it will bond. I'm going to give it away now. Group 5, it becomes -3 because it has accepted 3 electrons from somewhere. So it's gained 3 negative charges. Now it's -3. So nitrogen is an example there. let's look at oxygen. It gains 2 electrons to become happy. So it becomes -2. Because it's gained 2 electrons from something on this side. And you can see the clear difference. You have the metals on the left-hand side, and for the most part, you have non-metals that accept electrons on the right-hand side. Group 7, fluorine, it accepts 1 electron because it already has 7, and now it's happy. It's stable. So, when we look at what reacts with what, all of these charges have to balance out to 0. So, magnesium and oxygen MgO. Because we have 2 plus here, or +2, and over here we have 2 minus. So +2 plus -2 equals 0. So back to sort of grade 7, 8, positive and negative integers. And it has to equal 0. Now, that's something to go through later on, the seminar series. But you can see now why things bond together. And this is one kind of bonding between metals and non-metals, but we can go through the others later on. That's why things react, because things react because they're wanting to get to this state. They want to get to stability. They want stability, they want happiness, they want family. They want 8 electrons in their outer shell. Because if they don't have that number, they start dancing around trying to find them. So, redox reactions. So if a substance gains oxygen during a reaction, it is said to be oxidized, which is another way for saying if it loses electrons. They say when things rust, they become oxidized. So they're losing electrons to the surrounding air. If it loses oxygen during a reaction, it is said to be reduced, or if it gains electrons. So oxidation and reduction, or redox. So if we look at copper oxide plus hydrogen, okay, substance gains oxygen. Okay, so the hydrogen gains oxygen. So it is reduced. Sorry, it is oxidized. Copper oxide, if a substance loses oxygen during a reaction, it is said to be reduced. So, I don't even think I was sharing that last bit of the screen because I was doing the board. Okay, I will see you all next Friday. I'll put up a catch-up session of the session that was supposed to happen last week, and then we'll continue on next week from there.